Okay, we are going to present our work entitled Joint Noise Reduction and Listening Enhancement for Fluent Speech Enhancement. So we all know speech enhancement focus on improving the quality and intelligibility of the degraded speech. Depending on the usage scenario, we can roughly divide the speech enhancement into two subtasks. The first one is noise reduction, and the second one is listening enhancement. In a typical speech communication scenario, as this figure shows, in the left side, which is fine side, the microphone signal receives the mixed signal of speaker's voice and find background noise U. And this signal is captured by microphone. And the noise reduction is a task to modify such noise signal to recover the clean speech from the noise one. And in the right side, for listening enhancement part, that speech message transmitted from fine side, and this signal will be played out by the loudspeaker. Then the listener can hear it. But in practice, sometimes we are in a noise environment, so it would be difficult for the listeners to hear the voice. And also in this scenario, we cannot suppress noise by signal processing techniques. This is because the noise source is physically present in the listener side. So in order to compensate for the intelligibility loss, listening enhancement is a task that modifies the speech signal only to make it sound clear. And in this work, we are going to investigate a so-called fluent speech enhancement task. As we introduced before, given a condition that noise exists in not only the fine speaker and also the near listener environments, we will have to carry out the noise reduction and listening enhancement modules sequentially. So the question here is, how can we combine these two modules? Is the disjoint pipeline processing better, or we should jointly optimize these two modules under a unified framework? And before discussing the details, let's first reformulate the fluent speech enhancement using a signal model. So as this figure shows, the microphone signal is noted as X. It's composed of speaker's voice S plus the fine noise U, and it is processed by the noise reduction module. The output is STD, and this signal is transmitted to the near side. We have a listening enhancement module LE to process it to further improve its intelligibility. The output is denoted as Y, as an enhanced speech. And finally, the signal observed at the listener end is denoted as O, which is equal to the signal Y plus the near noise U, V. So our goal is to improve the listening experience for the listener side, which is the intelligibility of signal O and the quality of signal Y, by designing the effective noise reduction and listening enhancement modules. So this is a diagram of a proposed method, which is composed of three main modules. The noise reduction module is to suppress the noise. The listening enhancement module is to further improve the intelligibility of a denoised speech. And we also have a noise token module that is used to extract noise embedding and informs other modules of such fine environmental information. And for details of each module, we will only have a very short introduction here due to the time limit. If you have interest, welcome to see our poster. So for the noise reduction part, the main architecture we use is convolutional recurrent network. The next is a listening enhancement part. The module is constructed as a GAN model. The diagram of the generator part is given here. It consists of a few 1D CNN blocks. And lastly is a noise token module. This module is to encode the fine environment information and generates the corresponding noise embedding. We believe both noise reduction and listening enhancement module can benefit from such additional information. For example, by exploiting the fine noise knowledge, the listening enhancement module can be guided to avoid amplifying the time frequency regions that contain much less noise. So the training objective consists of three terms. The first term is intelligibility loss, which is defined in this equation. By diminuting this loss function, the listening enhancement module has to produce the enhanced speech, which can reach intelligibility score as high as possible, close to the maximum apply. The second one is similarly the quality loss, and the third one is speech denoising loss, which is SISR, calculated by comparing the denoised speech with the clean reference. And for experiments, we use hardware synthesis for training and also for test. Regarding to the optimization targets, we introduce 3 intelligibility metrics and 3 advanced speech quality metrics. And here is the result on intelligibility scores. The first line is the plain noisy speech without any processing. And next 2 lines is the systems we apply only noise reduction or listening enhanced module to the plain noisy speech. The next 2 lines is the so-called disjoint pipeline systems. And in the DSP pipeline systems, we use DSP-based methods as a noise reduction and listening enhanced modules. And similarly, we use neural network-based systems for neural pipeline systems. The last 2 lines is called joint methods, in which we jointly optimize the noise reduction and listening enhanced modules within a unified framework. So from this table, we can see applying only noise reduction or listening enhanced module doesn't increase the intelligibility at all. And we could see the joint method consistently outperforms the disjoint pipeline methods. And finally, by benefiting from the noise token, the joint plus NT denotes for the noise token module. So the joint plus NT systems achieves the overall best performance. And this is a similar result on the quality scores. And we can see the joint methods preserve speech quality very well compared to the pipeline systems. And this is the result on subjective preference test. 20 native speakers were recruited to listen to a pair of samples and select the one sounds clear in terms of intelligibility or better in terms of quality. And still we could find a proposed method, which is joint plus NT method, performs best. And here is some audio samples. The plain noise speech.
The corner store was robbed last night.
If it is processed by DSP pipeline system.
The corner store was robbed last night.
Processed by neural pipeline systems.
The corner store was robbed last night.
And processed by joint systems.
The corner store was robbed last night.
Last processed by the joint plus NT noise token model systems.
The corner store was robbed last night.
So you may feel that the speech is processed in a way that the noise is suppressed and also intelligibility is improved. So last, for conclusion, we propose the joint framework integrating noise reduction with listening enhancement to address a so-called fluent speech enhancement task. And under this joint framework, these 2 modules can be jointly optimized, and it achieves significant intelligibility gain while preserving speech quality very well. And that's it. Thanks for listening.